Do you hear me?
Yeah.
Yes. Don't sleep, please.
Yes, of course.
In this case, even of course, in this case, good morning, people. Nice to have you at this lecture. And we'll finish today the topic that we studied last at the previous lecture, propositional logic, and maybe we'll start the next one, because at first we were a bit too slow, but now we have to pick up the speed. And also, I hope that you registered your attendance. Did you? Because many students think that registration is the first thing they have to do. Okay.
Yes,
So
we did.
you did. Do you hear me all right?
Yeah.
Yes. Can I speak not so loud? May I speak? May, not can. I can, but may
Yes, okay.
Yeah.
I? Yeah.
Yeah, of course.
Okay, because I am afraid my voice is too shrill, irritating students and so on. That's why, well, I'll try to speak in a calm, quiet, well, soft voice, if I can. So, propositional logic. This here we will learn how to present formally statements or sentences in natural language, but not all sentences, but sentences that may be called statements. And in order to find out which of them are true and which of them are false. So we'll see what can be done by means of mathematical logic. So first, definitions. Statements. A statement is any sentence that can be true or false, or they say has a truth value. Well, I said about it at the previous lecture, but I remind you. For example, Kharkov is a city. Well, true. Now it is summer. Well, a statement which is false, but also statement. Some birds can fly. True. So all these are examples of statements. Go home. Well, we cannot say if it is true or false. It is an order. That's why not a statement. What is your name? Question. We cannot say true or false. A question is true or false. It's not a statement. So we don't consider them in the mathematical logic. What I'm saying is not true. On the surface, it looks like that it is a statement. But if we think a bit, then if it is a true statement, then it must be true about what I said. I'm lying. So, but if it is false, then what I'm saying is true. So it is contradictory. It is a paradoxical sentence. We are doing our best to avoid such sentences in our schemes, logical schemes. A barber shaves everybody who does not shave themselves, who do not shave themselves. Well, it looks that, well, everything is a narrative sentence, not a question, not an order, but still. And what does he do about himself? If he shaves himself, then this is false. If he doesn't shave, himself, then he must shave himself. That's why there is a contradiction in what is said in the inside. It is paradoxical. Statements can be simple or compound. Statements, simple or compound. Examples of simple statements. Today is Friday. Well, it is false. It is sunny now. Maybe true, maybe false. Depending. 5 plus 3, 2 plus 3 equals 5. Well, 2. 2 plus 2 equals 6. False. This narrative, повествовательные, narrative sentences have the truth values. The values may change in time. Now it is sunny, and 2 hours later it can become cloudy. It's not forever, but at the moment it may be true or false. Compound statements. Compound. They are made of one or more simple or compound statements that are linked. These compound statements that are parts of the general compound statement, they are linked together by connectives. Connectives. 5 basic connectives: not, and, or, if then, if and only if. These are 5 basic statements. Examples of compound statements. It is not Monday. If there is not, then it is compound because the statement was made from the this statement was made from the statement is to it is Monday. It is raining and the sky is cloudy. Also 2 simple statements. If it is raining, the second statement, it is cloudy, connected by and. If today is Saturday, then I do not have to go to work. Here, if then connective connects to simple statements. Today is Saturday, and the second statement is compound. I do not have to go to work because there is a negation. It is a negation of a simple statement. Another, I have to go to work. I have. So simple and compound are connected by a connective into a more, how to say, complicated, complex compound statement. 5 by x equal 5 if and only if x equals 1. Okay. If x equal 2 and y equal 3, then x plus y equals 100. Okay, another. Of course, here this statement is true and this is false. But okay. And one more example. The sun is not shining. Is not shining. If and only if tomorrow is Saturday and there are no clouds in the sky. Well, I put one more sentence here. Example of a compound statement, just to say, to note, to draw your attention that a compound statement does not have to make much sense. Normally, people don't connect sun shining in the sky with if it is Saturday or not Saturday. They are not linked events. And here a formal definition of a compound statement. Formal. It is done by oh my god, induction. Inductive, yes, inductive. All simple statements are compound statements. We consider them compound statements already. Okay. If S and T are compound statements, simple or actually compound, then S capital and T capital, not S capital, is a compound statement. S and T is a compound statement. S or T is a compound statement. If S then T is a compound statement, S if and only if T is a compound statement. So once again, S if and only if T. So is a compound statement. And these are two base case. The simpler compound statements. And after that, the inductive step here, how we create more complicated. And the third step, nothing is a compound statement unless it can be obtained by a finite number of applications of steps 1 and 2. So we can just now take not S and S and T and connect them by one of these connectives and so on, and we'll just construct more and more complicated compound statements. Okay. Finite number of steps, applications of steps 1 and 2. Note, mathematical logic cannot tell if a simple statement is true or false. No, it is outside the scope of the mathematical logic. This we must decide by other means. Well, by experience or by the opinion of people whom we trust and so on, but we have simple statements we must tell that this is true, this is false. The goal of the mathematical logic is to tell us whether a compound statement is true or false, depending on the truth values of its simple statements. Now we'll speak about how we build formulas, but formulas are built with from variables. But what is a variable here? Example, today it is Wednesday and it is raining. So we have one statement, actually sentence. And if we just replace n by a symbol or, then it's not much of a formula. So to represent such a statement in symbolic form, we replace this sentence by a variable p, by a variable statement variable p. And this is another statement variable p, not q. Different statements, different variables. That's why p, it is a replacement of a symbol substituting this sentence. We feel that the whole statement is true if both P and Q are true. You see, now we can speak quite conveniently. P and Q, and without saying both today it is Wednesday and it is raining are true. No, P and Q are true. The structure of the above, the structure of the above compound statement in symbolic form is as follows: P and Q. And is a logical connective. Here, P and Q are simple statements. Note, in mathematical logic, it is the logical structure, like this logical formula, of a compound statement that is important, not its individual simple statements. Like today it is Wednesday. Instead of P, we can just use some other sentence, substitute here, or this formula can represent many statements made by this pattern, or by this format. May I ask you, people, do you follow me? Do you understand what I'm saying?
Of course, we follow.
Yes.
Yes.
Am I speaking too fast, maybe?
No.
No.
No, you're
Okay.
fine.
Okay. In this case, great. But don't sleep in this case. Here, P and Q are simple statements. Так. So the logical structure of a compound statement, that is important. Not what is actually the actual statement instead of P, and actual statement instead of Q. For example, I'm a teacher and 2 plus 2 equals 5. Not much of a sense. Not much of a sense in this sentence. But still we see that this is simple statement, this is simple statement. This is, of course, true. This is, this is, of course, false. And this, well, we have to decide which is true or false, depending about who is I. So what I'm saying, that P represents the sentence, but its value of P is true or false. And it's not always clear to students. The value of the variable is true or false. Okay, so here may be true and here false. It is a table and it is evening, and so on. All the above, all of them, these statements, have the same logical structure, P and Q, and may be viewed as the same statement from logical point of view. Logical point of view. Not in the novel, not in the poem, nope. But from logical point of view, all this, and this one, they are the same logical statement. Okay. The precise meaning of each of the 5 basic connectives is defined by such truth tables. Truth tables. This is a table of the conjunction represented and this is the symbol in the formula. Well, logical. It was logical product in the 2-valued algebra. So P and Q can take values true and true, and the value of the compound statement is true. Here, value of P is true, value of Q is false, the value of the compound, now I say value and repeat it again and again, of this compound statement is false. False and true, here false. False and false equal false. Well, you see same for sets of values, truth values, and a bit later you'll know that this is this set of values assigned to a statement variables is called interpretation of this formula. So if P says something that is true, if Q says something that is true, then the whole statement is also true, though maybe the meanings of these sentences, well, denoted by P and Q, are not related, and so on. Disjunction. Again, here the standard set of interpretations of the formulas. Formula of two variables or sets of two variables of these simple statements. Again, you understand that it will be false when both of the statements are false. Negation. It's simple. Conditional. If then, it is in the natural language sentence, it will be if then, or I will give you some equivalent. How to say word combinations that have the same meaning. So here, it is if then always true, only it is false when P is true and Q is false. And false and false, never mind what is the value of the Q, what follows from P. If P, then Q. So what follows from P? What follows? If P is false, we may just consider that any conclusion is acceptable. That's why in both cases it is true. Of course, if these P and Q true, and here I will say about this assignment a bit later. Biconditional. Again, same interpretations, and the compound statement made by means of this biconditional connective is true when the values of both simple statements are equal. True and true, it is true. False and false, it is true. But if one is true and another is false, true, and vice versa, then this is not the whole biconditional statement is false. Note sentences. If P then Q, sentences made by means of these connectives. P only if Q, P implies Q, and some others all have the same logical meaning. Logical meaning this conditional pattern of building this statement. Note lines 3 and 4. These 3 and 4 in the table for P implies Q represent such a common sense concept. If an assumption is wrong, P is assumption, we assume that it is, well, if this, we assume that it is there, and this conclusion. So, if the assumption is wrong, then the conclusion is acceptable. Any conclusion is acceptable because nobody bothers to consider it. Nobody cares for such, pretense to speak or to think logically. There is no logic in this, in such, well, talks. Example, if 2 by 2 equal 5, then I am the mother of Napoleon. If 2 by 2 is 5, which is false, then I am the mother of Napoleon. Well, we assume, let it be, just leave me alone. True, we take it. If 2 by 2 equal 5, then 3 by 2 is 6. Also true, because we don't want to start proving something with a statement premise, which is false. In such cases, we should not consider what follows after them. Or normally they write it briefly and concisely. Explanation. Implication is defined by such a truth table, to make proof procedures, about which we will speak a bit later. Consistent, proof to make proof procedures consistent. And what do we mean by consistent here? To get only right conclusions from true premises. If premises are true, we are supposed to get the right conclusion. Only in such a case. And very often they say it even simpler. For convenience. And again, for convenience of proof procedures, to make them simple, for convenience. Here are some examples of transforming compound statements into symbolic forms. John is in the library, or he is not at the bookstore. So let P stand for, represent John is in the library. Q denotes John is in the bookstore. The symbolic form of this statement is P or not Q, because Q is it is not negative form, it is positive. Actually, affirmative statement. And here we have a negative statement. And here also negative. So we convert this affirmative into negative. If it is Monday, or it is raining, then we can go to the store. Another sentence. Let P stand for today is Monday. Q. So today is Monday. Q. It is raining. Z. We can go to the store. Then the symbolic form of this statement is as follows. P or, not Q, implies Z. Z, they say Americans, Z, English people. Maybe not now, but when I was taught English, they said Z. Example. Let P denotes I study. Q denotes I will pass the course. Okay. The formula. P implies Q and not P implies not Q. Is the symbolic form of this statement. is the symbolic form of the statement. If I study, then I will pass this course. And if I do not study, then I will not pass this course. Well, we'll speak later about the relation between the P implies Q and not P implies not Q. Actually, they don't have the same logical meaning. They denote different things. But well, I was free to write any formulas to connect them, and after that to interpret them as a sentence. Note, letters P, Q, and so on in symbolic form are called statement variables of the compound statement. And here, well, there are some self-test questions. You will read them later. And if you see, if it is easy for you to answer, if you are confident in the answer, if you are, great. If not, just return and read once again. Okay.
Извините, а
Read
можно?
once again in order to answer them easily. But here, because here the end of questions, it's better to just and here to separate the continuation of the explanation of the material. We can find the truth table for an entire compound statement. Here, a compound statement, P and not Q. So simple statements, P, Q, and here. Here I started to write as we are used to do in two-valued logical, two-valued Boolean algebra. F, false, false. Well, normally it is denoted by 0, 0, 0, 1, 1, 0, 1, 1. But here, well, since we are studying propositional logic, we use these symbols. And not Q. It is, of course, the reverse. False, true, true, false. Well, here the values of false, of not Q. And after that, here, P and not Q. So we take the conjunction of this false and true, false, false and false, false, true and true, true, and true and false, false. Okay, like that, exactly as we found the truth, constructed the truth table of two-valued Boolean algebra. Definition. Here, a new concept, important. At first, we will not see. Why do we actually? It is not definition for the sake of definition. It will be used in proving logical consequences from a set of statements. Actually, what conclusions could be made? Definition. A compound statement that is always true. So, statement made by means of connectives. That is always true regardless of the truth values of its variables is called a tautology. Such a statement is logically true because of its pattern, because of its pattern. So tautology always true for any interpretation of the formula. A definition: a compound statement that is always false is called a contradiction. Contradiction. Such a statement is logically false. Logically. Example: such a statement, compound statement, presented by such a formula, is a tautology. So we write here a set of interpretations of the formula, values of P and Q. After that, here the value of P or Q, here, P or Q. And after that, from P implies P or Q. If it is false premise, P, then never mind what is the value here, it is true. False, never mind what is the value, it is true. Now here, P is true, but luckily the value of the disjunction is true. From true implies true, true, and here again, same thing. True and true, the same true. That's why, whatever is the interpretation. A tautology is always true because of its logical structure, and not because of the meaning of its individual simple statements. We don't care what is instead of P. And here, in an example, this formula, not bracket P and not P, implies Q. It is a contradiction. Again, we make the truth table. PQ, we write the list of interpretations. After that, P and not P. P and not P. Of course, P false, then false. False and 1 and true. Again false. True and not true is false. And after that, true and not true, again false. So it is this formula, sub-formula, is always true, false. But if the premise here is always false, this implication is always true. That's why look here, what is before conjunction in these square brackets. We have all true here. But after that, we apply the negation to these true values. We get all false values. So formula, which is an example of a contradiction. Always false, never mind what is the meaning of P and what is the meaning of Q. I mean, what is the sentence? And what is the value of this sentence, true or false? Never mind. It is always not true because of its logical structure. Theorem. Now theorem. 1. Let A and B, A capital and B capital, be compound statements. So they are compound statements, meaning that they are made of, as presented by formulas that include some statement variables. And these variables are true or false. If the compound statement A, and this implication A implies B are tautologies, then B is also a tautology. B is also a tautology. Okay, proof by method, or will prove by the method of contradiction. Suppose A and A capital statement and A implies B statement, both statements are tautologies. Tautologies. But B is not tautology. But this B is not a tautology. Okay, and here I remind you the meaning of the implication. The meaning of the implication that it is false only if A is true and B is false. In all other cases, it is true. Also, some how's the explanations or comments. A and B are compound statements. So A, it is some formula or function of statement variables x, y, z. Each of them denotes some sentence, narrative sentence, f prime. And B is presented by another formula, which is of the same variables, by the way, x, y, z, x, y, z. So we have to here two statements about same things, x, y, z, x, y, z. And this formula we denote by f double prime. Double prime. We assume if that B is not a tautology. So it is possible to assign such a truth as some truth values to x, y, and z here. So that B in the formula f double prime of this x, y, z is false. If we assume B is not tautology, then there is some interpretation of this formula that brings the value false. We have to assume same values in A, but here we have same values, because same statements. Now for these values of x, y, z, A implies B is a tautology, so it's true for all interpretations in always, whatever is the value of x, y, z, here and here, and in this case it is a tautology. And B, for some interpretation, is false. It is possible only if, so, just a moment. A is true for some interpretation, and B is false. B is false. It is possible, but the A implies B is true. Only in these cases, if A should be false for the same interpretation, This is what it says. It is possible only if A equal also F. One of these lines. In A belongs to one of these lines. No, actually, B false. A must be also false to have it true. But it contradicts to the initial condition that our A is capital, is a tautology. So A is a formula, a function of x, y, z, and is T constant for all interpretations. This contradiction proves that our assumption, we just here, it is given to us through tautology, but we assumed this is false. it contradicts to our what was given to us. This contradiction proves that our assumption P is not tautology. This was assumption was wrong. Was wrong. In this case, if wrong, then it must be a tautology. End of proof. Okay, you will see how we'll use it later in some proofs. If in a tautology we replace some statement variable like x by an arbitrary compound statement, then the resulting statement is also a tautology. Given P or not P. It is a tautology because it is always true. We replace variable P by P implies not Q. We get a new tautology. P implies not Q or not. P implies not Q. If we can... sorry?
Простите, а перемена будет?
А уже пора, да?
Да.
Да, сейчас. Сейчас вот я вот эту вот фразу закончу. Все. We can check it by making truth table that it is a tautology. Make it always true. Thank you for 5 minutes. 5 minutes. Have a break. Relax. Thank you. Okay. Unfortunately, this time nobody reminded me to start recording. I do it right now, with your permission, of course. With your permission, of course. Okay. May I ask you if everybody of you sees this page with the logical equivalence? Do you see it or not?
Yes,
Yes.
we
Yes,
see.
great.
Yes.
Yes, because thank you. Because I started recording and it might interfere with the translating the conference. Okay, now here another example of substituting a an arbitrary formula like here into a formula which is a tautology. We get another formula here instead of P, this one, and after that Q we leave it as it is, and here again P, this one, and it is also a tautology. We can prove it here at home. Please, if just try and practice in these home assignments. But now it's time to speak about the possibility or the method of transforming sentences of natural language in such a way that these transformations preserve the logical meaning. If the original one was true, then after transformation, it will remain true. If it was false, after transformation, it will be also false. They say in equivalent way. So logical equivalence. Logical equivalence. Definition. Two compound statements, A capital and B capital, are said to be logically equivalent if they always have the same truth table. We denote the relation of equivalence between formulas, like by these three parallel lines, but also just sometimes by the symbol of equal. Because here I have to insert and equal type from keyboard. Example, not P or Q. It is equivalent to P implies Q. Yeah. Meaning they have the same truth tables, these two formulas. Note, in the truth table of A capital and B capital, the statement variables must be placed in the same sequence in order to compare tables correctly. It's not like false, false first, false and true second, and in the second table we'll start true, true, and so on. In this case, well, it's difficult to compare them correctly. Theorem 2. That was the first theorem about the what? B must be a tautology also if A and A implies B tautologies. This was theorem 1. And here, theorem 2. The compound statement A and statement B are logically equivalent if and only if the compound statement A imply if and only if B is a tautology. In a sense, A and B are logically equal. It doesn't mean that you say something that A, statement A, and if somebody rejects it, doesn't understand, and so on, you represent the statement B only because it is logically equivalent. But the meaning, the sense may be quite different. But from logical point of view, equal. Laws of propositional algebra are examples of logically equivalent statements. Laws of propositional algebra. We don't discuss, define what we mean by propositional algebra, but a bit later. Let P, Q, and R be statement variables. T denote any tautology, any compound statement with this, which is true, constant. Let C denote any contradiction, which is always false. Properties of a contradiction and tautology are as follows. Any formula P or contradiction, the logical value of this P or C is the same as P. P and tautology, the logical value of this formula is that of P. P or T is equal T, P and C is equal C. So if we just are not sure how to memorize it, then C might stand for 0, 0. If we denote, but here just any statement. Here any statement, many sentences. There are very many compound sentences that are logically false, are constantly false. So just C and P, it is many sentences that may be true or false. Here many sentences, but the logical value is 0. Here logical, many sentences, logical value is true. So it's not just true or false. They represent sentences that are true. Okay. Properties of negation. Not T equal C. So T might be taken as 1 just for memorizing purpose. C as 0 in pervaded logic and everything. Not C is T, P or not P. It is always a tautology. Patient is true or who? Patient is alive or dead. Of course, something. Patient is alive. Patient is not alive or dead. It is always true. This is the wisdom of many people. Okay, P and not P equal contradiction. And after that, not P, it is the same as the statement P from logical point of view. Other laws or properties of connectives. Laws, now they describe properties of connectives, are also familiar from the set algebra and the two-value Boolean algebra. Commutative, associative, idempotent, distributive, De Morgan's laws. For example, property 1, 1, this 1, 1. formula, says the following. Any statement P or any permanently false statement is true if and only if P is true. Well, it's evident. Or the truth value, or another just point of view on this formula. The truth value of any statement P is the same as the value P, a value of P or false statement, Never mind what is the meaning of P and C. What is the meaning of P and C? It's like this. That's why sometimes in order to start proving something, some tricky people just take a statement that is, well, to start, that it is true, and after that, if it is true, or they just add the statement that may be true, it does matter, but well, since it does not change the true value of this, connects as if this is true, and after that, somehow later in the logical sequence of proofs, will use it already as proven C, C as proven true, and after that. So this is one of the methods of using these contradictions to, not for correct proof, logical proofs, but for a sequence of statements that looks like a proof, but which is not. Now we can talk about propositional algebra. And what is it? Set of propositions plus connectives, or and not. Its laws are just patterns. Its laws of this algebra are just patterns for making compound statements. Do you know what is pattern? Schablone, pattern, schablone. Now, for making compound statements are sentences of natural language with the same truth values. But you say, well, here we see only 3 connectives in the algebra, but there are 5 basic connectives. In propositional algebra, connectives, implication, and conditional, connective, and biconditional connective are considered as shorthand notations for some compound compositions or compound statements made of disjunction, conjunction, and implication. P implies Q. It is equivalent. You see here I write equal, equivalent. Not P or Q. And here, now we use only the connectives that are, well, convenient for transformations. Biconditional. It is equivalent to P implies Q and Q implies P. And that's why, okay, the first thing when you get a formula with these connectives, conditional and biconditional, and you want to transform them, maybe simplify, maybe make it more clear, the first thing you have to get rid of a biconditional connective, and after that to get rid of by this equivalent formula, and to get rid of such conditionals by this method, and after that you're ready to apply these associative, idempotent, distributive, commutative, and so on properties of connectives. Using these properties, it is possible to transform statements of natural language without changing their true false value. True false value only. Given example, given a compound statement, it is raining or it is snowing. P or Q. This is the logical form. Write a negation of this statement. So here it is simple. It is raining or it is snowing. It is no ambiguity, clear, but if negation, not P or Q. Okay. Not true that it is raining or it is snowing. Well, we don't understand this nor. It applies to everything after that follows after true. Or maybe not it is raining or it is snowing without negation or something. Formula shows that yes, negation is applicable, should be applied to P and Q. But if we transform it like this, not P and not Q by De Morgan laws, then the statement is as follows: it is not snowing, and it is not raining, and it is not snowing. Then there is no ambiguity that it is nice weather, nice weather. And here we are not sure if it is so. Statement: it is raining and it is snowing. Here it was or with negation. It's negation, not P and Q. It is not true that it is raining and it is snowing. Again, for the same reason, it is ambiguous. Not one way to understand it. What do we mean? But if we transform it in equivalent way, De Morgan law, not P or not Q, it is not raining or it is not snowing. Then there is one understanding. Okay, now, example, what is required to prove that this P implies Q has the same logical meaning as not Q implies not P. Implies not P. Such a statement is called original statement. Well, it is given. And this, we said it is equivalent. Contrapositive statement for the original one, for the original conditional statement. That was what was the conclusion. Now it becomes premise with negation. And what was the premise? It now is used as a conclusion with the negation. Okay. Prove that these two formulas are equivalent. And this formula, P implies Q, if and only if not Q implies not P, is a tautology. So, two things to prove: equivalent and here tautology. How can we prove? Of course, by making truth tables, And yes, we'll see. Just you have to remember, if somebody just says, что-нибудь такое. Если я не ваш начальник, то вы меня не слушаетесь, не подчиняетесь, то вы мне не подчиняетесь. Так, ну с этим мы согласны и говорим true, true, true. Но если я ваш начальник, то вы мне подчиняетесь. Некоторые и очень многие пытаются что-то логически доказывать. Вот вы сейчас же со мной согласились, а теперь, если я ваш начальник, то вы мне должны подчиняться. Всегда. А вот как раз по логике-то, это два вот этих высказывания не эквивалентны. Не эквивалентны. Они могут быть, так сказать, одинаковые или не одинаковые, в зависимости от вот этих значений P and Q, true, false. А это вот типичная схема, ну, что ли, введения в обман. Потому что надо взять отрицание не первого и потом следует не второе, а наоборот, взять отрицание второго и из этого следует не первое. Вот это, да, логический эквивалент. Если мы с этим согласны true, то и это true. Если с этим это false, то и это false. И это мы должны увидеть с помощью таблицы. Ну, как мы знаем. А вот интересные, так сказать, вот уже более такие содержательные задачи. Given a statement. If x equal true, then x squared or raised to the power 2 is 4. It is certainly true. We know it, that it is true. Why? Because from mathematics. Certainly it is true. It's contrapositive statement. Well, which is not that evident. If x squared not equal to 4, then x not equal to 2 is also true. Why? Why? Because we proved in exercise 3 here that these two formulas are equivalent. That's why if this is true and we know, then this is a contrapositive statement made by this pattern. It is also true. Okay. Another example, something like this. Given, if x is positive and x squared is equal to 4, then x is equal to. Okay. Well, it is certainly true. We have no doubt about it. We studied at school. And the formula is P and Q implies R. Implies R. Its contrapositive statement is also true from here. And what is contrapositive statement? If x not equal to 2, then not true that x is positive and x squared is 4. It is not R, implies not, P implies R. Or it is this is equivalent to not I implies not P or not Q. If x not equal to 2, then x is not positive or x squared not equal 4. Also, well, the logic tells us this story, and our knowledge of mathematics and tells the same thing. Here some more prove that if n squared is odd, then n is odd is true. If n squared is on, then n is true. Well, we are not sure how to start proving this, at least me, at least for myself. And in this case, it is easier to use the contrapositive statement, which is, if n is not odd, then n squared is not odd, And what does it mean? N is not odd. N is even. Then n squared is even. So we just, not odd is even. N is even. Okay, so if n is even, in this case, we can present, and we'll prove it. If it is even, then it can be presented like n equal 2 to the power k for some integer k. Right? Now n squared is 2 to the power k raised to the power, 2 to the power, 2 by k raised to the power 2. It is equal to 4k squared. But 4, we split this coefficient 2 by 2 to the power k. And we now see quite clearly that n squared is also even. So if n is even, then k is even. Now, if n squared is even, k is even, from here it follows, if just a moment. What did we prove? What was it that we proved here? We proved here. From here it follows that the original statement P implies Q is also true, and this was this that we had some problem in proving. Okay, that's why sometimes it is easier to start proof from contrapositive statement if we know how to use it. Okay, that's it. And here, one more example. You will see it yourself. People, do you have questions? Prove that. Oh my God. Here. This moved and this was. Do you have any questions? Sorry?
Да, есть один.
Давай.
Вот по поводу примера в пятом. Пример 5.
Да.
По поводу строчки, сейчас я ее найду теперь. Вот там, где if x не равно 2, then, значит x не позитивный, не положительный, и x в квадрате не равно 4. Почему это правильно?
О май год. Не равно 2. 3, скажем 3. 3 в квадрате это равно 4? Может быть равно 4?
Нет.
Нет. Только x равно 2, 4. Скажем x минус 2. Но это же минус 2 не равно 2. Поэтому есть только одна возможность. Если x не равно 2, то x and here x is positive. The second condition. X is positive. Поэтому мы, так сказать, минус 2 не рассматриваем сюда. Здесь же 2. Positive. И вот это вот. Разве вы не согласны?
Тут согласен. Не совсем понимаю, там, где выражение контрапозитив, которое через строчку. Тоже, то же самое, только наоборот.
Сейчас. not x implies
Вернее, которая уже раскрыта.
not. This is P positive, and this Q, not Q. Logically equivalent. Not R here implies, and here by De Morgan law, not P or not Q here. Теперь, now we are trying to read R. It is x equal to, not R, x not equal to. R, x equals to, not R, x not equal to. Then, not P, x is positive, not P, x is not positive, negative. No, well, x is not positive, or x not equal 4. That's why if this is true, then either x is not positive, because it may be 3, 4, 5 or something. 1, it may be positive, but not 2. Then either one thing is true, either not positive, but if this is false, then we get to the second situation. X is square root, squared power is not equal 4. Like that.
Это я понял. Есть еще один вопрос.
Да.
Вот по поводу равно, там где, ну, с тремя, с двумя и двойной импликацией. Я как-то с этим не разобрался вот совсем в различиях.
Нет, вот это вот. Ну, это я действовал здесь, ну, как вам сказать. Вначале я хотел показать отношение эквивалентности. Но потом же я сказал, что этот знак, это надо включать все время специально куда-то залазить и его вставлять как символ. Его нету на этой клавиатуре. Поэтому дальше, когда я не знаю, на то ли я, вот ставлю здесь равно. По идее, надо было вставить 3 параллельных линии. Но чтобы поменьше возни, равно. Равно имеется в виду, что здесь таблица такая и здесь точно такая. Две одинаковые таблицы.
Да, здесь я понял. А вот страницы выше, там есть пример третий. Вот первая строчка, да. Вот там, где... Да. Тут совсем как-то непонятно.
Нет, так это просто задание. Я ж его не решал. Я его не решал. Это задание. Я говорю, что вот вам prove that, докажите. Вот эта формула эквивалентна этой. Ну а как? Вот здесь вот вы импликации PQ и 0,0, 0,1, 1,0, 1,1. Здесь вы строите таблицу значений здесь и строите таблицу значений здесь. И видите, что они, так сказать, одинаковые. Поэтому формула эквивалентная. Но потом еще к этому же, вот к этим двум столбцам надо добавить таблицу, столбец значений вот этой формулы. И вы увидите, что вот здесь, вот напротив вот этого двойной импликации, там будут одни единицы.
То есть то же самое, что эквиваленция, да?
Да, потому что раз здесь вот эти таблицы совпадают, но ведь тогда же, где же вот двойная импликация, это когда вот для совпадающих значений. Да, это будет давать единицу. А они везде совпадают.
Все, предельно все
это
понял.
Я здесь не строил таблицу. Ну, хорошо. Еще спасибо за... Так, секундочку. Что у нас тут? Ах, вы меня специально. Ну, секундочку. Тогда вот, что был наш lecture. 5 минут, извините, с вашего позволения, я все-таки начну. Valid arguments. Собственно, все вот эти вот рассуждения, вот, наши, это были для того, чтобы, показать, как с помощью аппарата формальной логики можно доказывать, логически достоверные доказательства строить. Либо, по-другому говоря, доказывать теоремы. Что-то мы берем с самого начала, а в качестве аксиом, постулатов мы говорим, что мы убеждены, что это, верим, что это так, и потом из них, исследуя совершенно, так сказать, формальными шагами, делаем вывод, приходим к выводу, который, доказательству теоремы. Вот. Но let us see how it is done by valid arguments. Valid – это годный, подходящий. И логически обоснованные доводы, вот это, valid arguments. Or, in English, use of reason to decide something or persuade someone. Persuade, убедить someone. Definition. An argument. Это я просто вас приглашаю потом почитать перед следующей лекцией вот это, чтобы... An argument is a finite collection, a sub 1, a sub 2, and so on, a sub n, of statements, simple or compound, followed by a statement A, capital. We denote an argument by such notations, two notations. Either this A1, these are, what is given to us, AN, and this is the conclusion, AN. Therefore, the horizontal bar stands for the word therefore. That is why, therefore. Or, if we want to write in one line, we can write A sub 1, comma, A sub 2, comma, and so on, A sub n, and some symbol, just after which the conclusion follows. And somehow we need to be able to prove that this logically follows from these statements. Each of the statements, A sub 1, A sub n, is called a premise.
Извините,
argument.
а четвертая и пятая группы не видят ничего.
Oh my God.
Первая, вторая, кто ничего не видит.
Что? И первая, вторая, третья не видят?
Да.
Oh.
У нас предыдущая лекция.
Ага. Okay. In this case, we
Your
have...
screen at exercise 3.
Ага. Okay. We have 2 minutes left. I will not resume it again. If you have questions about the previous, oh my God, now I have to be vigilant each time when I change the word. Something that I want to show on the screen to everybody. Oh. Okay, I will not start. It's too little. This is for groups number 1, 2, 3, and this for groups on. No. Now, please tell me, group 1, 2, 3, do you see the the screen with this previous lecture?
Yes.
Yes.
Ah.
We see.
And group 4-5,
Yes.
nobody alive. Okay. Please ask me any questions, and also I remind you that at 1:10 there is a consultation. There is a consultation. Please join everybody who wants, who has any questions. I will have more time to satisfy your possible curiosity. Okay, I just try to start my lecture again because now I have to be vigilant. I have to remember about too many things to start recording, to start showing every new window to both conferences and many steps. Very inconvenient. Okay, please, people, do you have questions? Do you have any requests? What do you have any problems with labs and tutorials? I can talk to and discuss it with my assistant. Anything? No. Thank you.
Everything is fine.
In this case, see you, some of you,